All right, so I want to go ahead and write all these out, right? So this is the stiffness matrix we're going to use for each element, and then later assemble all three of them. In this case, right, we got 3 elements. So we're going to use these little little stiffness matrix to make the big global stiffness matrix. And then the table, right? So we have 3 elements, 1, 2, and 3, which is just the bars, right? And we got to get all these values for each one, right, to fill in this matrix. And yeah, that's pretty much it. So determining the angle, I mentioned it in the previous video, but I'll go ahead and do it one more time. I always stick to going from the smaller node to the bigger node. In this case, right, 1's the smallest, 1, 2, 3, 4, they're all in order. So go from 1 to 3, don't go from 3 to 1. I'll show you how to do both, but just to be safe, right, when you're doing the matrices, it could get a little confusing once you start labeling the columns and rows. With U1, V1, U3, V3 in this case, or it will be U3, V3, or U1, V1, but always go from the small one to the big one. So let's go ahead and do element 1. It goes from 1 to 3, so we're going to using the positive x-axis, we're going to use this angle right here. So this angle, let's go ahead and find that. It's a 3, 4, 5 triangle, so that means tangent theta. That's how I know these lengths, just FYI. You could do, Pythagorean theorem, right? 30 squared plus 40 squared, you're gonna get 50 squared, but just FYI, it's a 3, 4, 5 triangle. So it's tan theta is equal to opposite, which is 40 over 30, right? Adjacent, and then theta is gonna be 53.13 degrees. All right, so that's this angle right here. And similarly, it's also this angle, right? Now, one more thing, let's convert. So the thing is, we're giving everything in inch, right? Inch, PSI, which is pound per inch squared. We got to get this converted to inch. This is going to be 600 inches. This right here is 600 inches. And this right here will be 240 inches. You're going to need it for when you do EA over L, right? Everything has to be in inches and pounds. So let's go ahead and write, we're going with the angle. So we're going to use this angle in this case. Now, if you wanted to go from 3 to 1, this would have been your positive x-axis, and you would have done 180 plus 53.13, because this angle is also 53.13, right? Trigonometry. So it would have been like, what, 220, 230 something, whatever it is. That would have been your angle. But because we're going from 1 to 3, our angle is going to be 53.13. And none of the answers are wrong. Even if, because this matrix is symmetrical, c squared, cs, cs, s squared. And same thing here, right? C squared, cs, cs, s squared. These 4 would just switch with these 4, but they're exactly identical. So if you're looking for just the global stiffness matrix, luckily determining which angle to use, whether it's the 220, 230, whatever, or the 53.13, you're going to be fine. Because the matrix is symmetrical. But once you start verifying forces and whatnot, stresses, that's when your signs are going to get you mixed up. So, and on the exam, I'm assuming he's going to want you to find the forces and stresses. So I would suggest always just stay consistent with this, okay? Go from the smallest to the biggest, and then use that wherever that bar is. That's the angle you use. So 53.13, if you get the cosine, you know what? That's fine, hold on. Let's go ahead and do the second one. So the second one, right, we're gonna go ahead and use this angle now, again with the positive x-axis going from 2 to 3. You could use this angle, which would be 270 plus this little angle right here, whatever that is. I think it's like 300, I don't know, whatever, right? It's 270 up to this line, and then this little angle, if you were going from 3 to 2. But we're going from 2 to 3, so we care about this angle right here. There's a lot of thetas, okay, just FYI, my bad. But that's just 180 minus 53.13, right? And that number is 126.87 degrees. They're all degrees, right? And finally go from 3 to 4. That angle is going to be a perfect 90 degrees. Again, if you went from 4 to 3, you would have done it with respect to the positive x-axis, and that would have been a nice 270, okay? But that's it. So let me stop it right here. I'll fill in this table, right? We're going to get the cosine of each number, the sine of each angle, not number, angle, cosine squared, then sine squared, then cosine times sine, and then EA over L. Now let's do the EA over L's first, just so you can see how I do it, right? It's just E times A, which is 90 times 10 to the 6. This is pound per square inch. This is inch squared, so it's just pound divided by another length, that's pound over inch. And they all have to be in inches, no feet, okay? So they give us feet here, but we have to convert. So if you do that, you will get 0.15 times 10 to the 6, 0.15 times 10 to the 6, because the lengths here are the same. So EA is the same for all of them, but length 3 is different. So that's gonna be 0.375 times 10 to the 6. I just want to leave 10 to the 6 alone, so I made these decimal, but don't worry, it's the same thing. All right, so I just want to go ahead and fill up the table, right? Take the cosine and the sines of each angle, 0.6, 0.8, 0.36, 0.64, 0.48. Same numbers here, just negative here and a negative there, and then 0, 1, 0, 1, 0. So that's all I did. That was step 1, so going back to step 2, going to step 2. For the first element, right, so this is our first element here. It's you get the EAL, right, according to the formula. So you get 0.15 times 10 to the 6. That's gonna be, again, this is where it's important. We chose for element 1, right? We chose going from 1 to 3. So we're gonna have U1, V1, U3, V3. And same thing here, U1, V1, U3, V3. All right, and that's pretty much it. We just go ahead and fill in the matrix values. So cosine squared, sine squared, cosine squared, sine squared for element 1, that is 0.36, 0.64, same thing, right? 0.36, 0.64. So 0.36, 0.64, 0.36, 0.64. It's really easy to get mixed up, be careful, okay? Then cosine, sine, negative, and then positive. So it's this number, just positive, negative, positive. So 0.48, negative 0.48, and 0.48. U3 and V3, right here, negative cosine squared, negative sine squared, my bad. For some reason I read these numbers. Negative cosine squared, all right, so it's negative 0.36. Again, we're looking at the first element, so these numbers right here, these 3. And then negative 0.64, and then finally a negative cosine sine, which is negative 0.48. So that's it, right? Symmetrical. So it goes down this way, 48, negative 0.36, right? This number, this number, this number, negative 0.48, and these two over here, so it's negative 0.48, negative 0.64, and finally this number is 0.48. Symmetrical, that's all it means. All right, so let's go ahead and do the second element, right? It's gonna look something like this. All right, so it's K2 now. That is also 0.15 times 10 to the 6 for EAL, 0.15 times 10 to the 6. And this is between nodes, element 2, right? We went from 2 to 3. So it's U2, V2, U3, V3. Same thing, U2, V2, U3, V3. There we go, make it look nice. Same thing, right? Just fill in the matrix just like we did with the first one. But now we use these numbers. So everything's the same except it's negative. So it's gonna be 0.36, 0.64, 0.36, 0.64. Okay, move it up in case you can't see, but it's right there. Now that's negative 0.48. Again, I'm just using the top matrix, using the numbers for element 2, and just plugging in 0.48, right? All right. Next ones is negative 0.36, negative 0.64, and finally it is positive 0.48, because negative and negative, right? And again, it's symmetrical, so just bring those numbers down this way, and positive 0.48. This one here is 0.48, negative 0.64, and negative 0.48. So that's that one. Now let's go to K3. And that's going to equal the EAL, so this one's different, 0.375 times 10 to the 6. And let's go ahead and do the matrix. So this one is element 3, so it's between 3 and 4. Remember, that's the angle we chose. And that's the reason I use the angle from small node to big node, because I just like to stay consistent. The small number here, the big number here. If I would have had to switch these two if I use angle 270, remember? But I mean, technically it's still right. Just I like to go from small number to big number. And U3, it's gonna be a little tight here, and there we go. All right, plug in, right? We're gonna use these numbers, c squared, s squared, and cs, which is 0, 1, 0. And so it's going to be c squared, s squared, c squared, s squared. It's going to be c0, so cs, negative cs, and cs. This is negative c squared, negative s squared. And finally, this is just 0, negative cs. So 0, 0, 0, 0, negative 1, 0. Cool. So now we got them. Let's go ahead and do the stiffness, global stiffness matrix, or the global equation at this point, right? It's a lot of writing if you do that separate. So it's gonna be, it's 6 nodes, right? X and Y. So it's F1X, F1Y, F2X, and we got F2Y, F3X, F3Y. Oh, my bad. And then F4X, F4Y. F4X, F4Y. My bad. So we had 4 nodes and 2 X and Y, right? So it's an 8x8 matrix. All right. So before we continue, we cannot add this matrices, all of them. So normally if they had the same number out here, EAL, we could. But in this case, this one's throwing us off. So now you have 2 options. You could alter just this one in a way that you'll have 0.15 out here. So this divided by 3.75, 0.375 divided by 0.15, you'll get a number, and you could just like kind of work with that number to fix this matrix up, and you'll have 0.15 all around. Or what I'm gonna do is I'm gonna go ahead and throw 0.15 inside and cancel it out here. So before we do that, it's gonna be a lot of erasing, right, for every single node or whatever, every little position. So let's go ahead and do the boundary conditions next, and that's gonna save us a lot of time. So U1, V1, U2, V2, and U4, V4, they're fixed. So we could just cancel them out. They're all 0. So U1, V1 is 0, right? And it goes this way too. So cancel all those. We don't need them. U2, V2, 0. So cancel those. Again, rows and columns, not just rows or just columns. And then finally, U4, V4 is fixed. So these are gone too. So now we're left with 12, I want to say, right? 4 here. Let me just go ahead and cloud them up. Okay, we got 4 here. I like to cloud them up just so I could see them. Sometimes it's real easy with all these lines and numbers. You could miss one. So if you cloud them up, you cannot miss that big ass cloud. Okay, so we're gonna cloud these. Finally, it's taking a little while, but we're good. Okay, so now what I'm gonna do is, so think of these matrices as like a equation, right? It's a number is equal to a number times a number, or a variable. So let's just give it variables. So in this case, K, I'm just gonna get into this real quick, is Z, right? Is equal to this number. Let's give it 2x. It's 2 numbers, right? 2x times your matrix Y. I just gave it some dummy variables. Now look, in this case, 0.15 is 2, right? I did this so you could see it easier, so you can see what I'm saying. 10 to the 6 is x, and the matrix is y. If you multiply, so this equation is pretty much saying z is equal to 2xy, right? That's the same as saying z is equal to x times 2y, no? It's the same number. So what we're gonna do is, instead of multiplying 0.15 to 10 to the x, we're gonna multiply 0.15 to the whole matrix and then just erase it out here. It's the same thing. So that's just something so you could see what's going on. So if you do that, 0.15 times 0.36, that's gonna give you a number. That's gonna give you, let me go ahead and do it now, 0.054. For 0.48, there's 2 of them. Sorry if the camera's shaking. My desk is pretty small. If you multiply 0.15 times 0.48, you will get 0.072 on both of them. Then 0.64 times 0.15, you will get 0.096. Now, this one goes, God damn, this goes away. Damn. So that's just 10 to the 6 times all this. Oh shit. Okay, cool. So we just continue doing it, right? These are the same numbers, just that these two are now negative. So I'm gonna go ahead and do that. Again, sorry if the camera's shaking, but there we go. So this is gonna be 0.054, 0.096. This is negative 0.072, negative 0.072. And again, we just erase this right here. That's all we're doing. We're just moving the 15 into the matrix. And for this one, right, now we multiply only this one in this case by 0.375. Not by 0.15, okay? 0.375, just to get a nice 10 to the 6 outside the matrix. And that's it, you know? Now we could go ahead and add these matrices. So they all have the 10 to the 6 as a common factor. So let's go ahead and do that. There's gonna be oh, what happened there? It's gonna be a huge matrix. All right, this is bothering me. Okay, so you got U1, V1, U2, V2, U3, V3, U4, V4. And then similarly, right, all across, U1, V1, U2, V2, U3, V3, and actually, you know what? Can I go ahead and make this a little bit spread out because we're gonna need the space. U3, V3, and finally U4, V4. Okay, so bring that down. Now, don't get scared. I know it's a huge matrix, but it's not that bad. Let's go ahead and do U1, V1. This is a displacement vector, right? U3, V3, U4, V4. All right, so that's the whole equation. So just like we did here, right, we're just gonna cancel the rows and columns. These are all fixed. Node 1 is fixed. Node 2 was fixed. And U4 was fixed. Well, node 4. All right, so same thing across, right? U1 is gone. V1 is gone. U2 is gone. V2 is gone. U4 is gone. And U5 is gone. So we only care about these 4 positions, right? U3, V3, U3, V3 for every single one. So that's the U3, V3, U3, V3. So we just go ahead and add them. So 10 to the 6, right? We could add them because they all have the same 10 to the 6 outside the matrix, so we're good. If you do the adding, 0.054 plus 0.054 plus 0 for position U3, U3, you will get 0.108. Add the next ones, 0.072, negative 0.072, that's 0, plus the 0 right here. So this one's 0, Same thing here, 0.072, negative 0.072, and 0. So that's 0. And then finally 0.096, 0.096, 0.375, add those three together. You will get 0.567. All right, so we're good. We got that. Let's go ahead and do, all these were 0, right? 0, 0, 0, 0. And that's 0, and that's 0. So we're looking for U3 and V3. Now we know the force at 3, right? It's another boundary condition. We have a positive 5,000, not just 5. Kip is 1,000, so it's 5,000. At node 3 in the positive x direction and a negative 20,000 in the y direction, okay? Right there. So it's positive 5,000 for x, negative 20,000 for y. So these two numbers, you could go ahead and make the two equations. You're gonna have two unknowns, U3, V3. Let's go ahead and solve that. So it's gonna be 5,000 is equal to 10 to the 6, don't forget that little number, times 0.108 U3 plus 0 times V3. So if you do that, let's go ahead, it's 5,000 is equal to 10 to the 6, 0.108 U3. Similarly, for the next one, it was 20,000, right? Let me go ahead and go back to it. It's negative 20,000 is equal to 0 times U3. Oh, 10 to the 6, sorry. So it's negative 20,000 is equal to 10 to the 6 times, parentheses, 0 plus times U3 plus 0.567 times V3. In this case, it's just times 0.567 V3. So if you do that, your U3 and your V3, in this case, we don't have to do like some crazy algebra to solve it, right? It's just straightforward. 0.4630 inches, and this is negative 0.03528 inches. Okay, so that's the answer. So now the next part of the problem says solve for the forces, right? What does it say? Verifies force equilibrium at node 3. And we'll do that in a second, right? It says, my bad, I was reading the other paper. The element forces. So we got to get that first, and then we verify the force equilibrium at node 3. So let's go ahead and do that. This is the equation for local element forces. I haven't done it in the other videos. I think one problem did ask for it, but I did it doing the stress method. It's the same thing, but if you want to use this one, this is how you do it. So this is the equation, right? Let me go ahead and write it down first. Give me a second. So it's CS0000 CS. It's kind of complicated, it looks complicated, but it's pretty easy. And technically, I'm gonna do the first one. So U1, V1, U3, V3. But pretend it's just a displacement vector for now, okay? So check this out. You multiply the matrices, right? So you'll get F1x, F3x. And if you don't remember how to multiply matrices, you might have to review it. But just real quick, it's like this. So this is a 2x2 matrix. This is a 2x4, row, column, row, column. So if you multiply them, the 2's cancel out, you'll get a 2x4 matrix. So you'll get 2 rows, 4 columns. So that's how you do it. It's C times 1 plus negative 1 times 0. That is just C. Next one, on the bottom one. Now I'll do the next one actually. So we'll just stick to the top row for now. So it's 1 times S, which is S, plus negative 1 times 0. That's just S. Next one. So it is, how do we do this? It's 1 times 0, which is 0, plus negative 1 times C. That's negative C. And then finally, 0 times 1 plus negative 1 times S. That is negative S. Same thing for the bottom, right? Now it's negative 1 times C plus 1 times 0. That's negative C. it's negative 1 times s plus 1 times 0, so it's negative s. And these are cosine sign, okay? And then it's 0 plus c, 0 plus s. So that's how you do that. And then displacement vector, right, is just, again, u1, v1, u3, v3. So let's go ahead and do it for every element. In this case, I was doing it for element 1, which is why I put 1 and 3, right? So for element 1, you're going to have f1x, right? It starts at node 1 again, because we chose it that way. So it's node 1, node 3 is equal to EA over L. EA over L, so it's EA over L, right? Oh, it's right here, I've already got it. So it's, I'm gonna go ahead and do 15 times 10 to the 4th to get rid of that, okay? Just, it's the same thing, 15 times 10 to the 4. So this is gonna be here, let's go ahead and plug in the numbers, right? It's gonna be 0.6, so this is where I get the numbers. 1 through 3 is nodes 1 through 3, that's element 1. So we're gonna use these numbers. For element 1, we're gonna use 0.6, 0.8. So it's 0.6, 0.8, okay? Then 0.6, 0.8, and then they're just negative here. 0.6, negative 0.8, negative 0.6, negative 0.8. There we go. Then multiply by the displacement vector, it's gonna be u1, v1, which is 0 and 0, and then u3, v3. So it's gonna be 0.04630, negative 0.0352800. Okay. All right. Damn, it's just long. So we're gonna go ahead and solve for that, right? So f1x of element 1 is equal to 15 times 10 to the 4. We're gonna have 0.6 times 0, 0.8 times 0, negative 0.6 times 4630. So that's gonna be negative, let me look at my number here, 0.02778. Okay, that's negative 0.6 times 4630. Then plus negative 0.8 times this one. That's gonna be a positive 0.02822. Do the math right here. You will get f1x of element 1 is going to be 66.6 pounds. It's a very small number. And similarly, if you get f3x, right, you don't need this number, but I'm gonna go ahead and just put it in there. The signs just switch, right? So the signs here are different from so the first row has different signs than the second row, right? So that just means this is gonna be a positive, and then this is gonna be a negative. So you're just gonna get a switch number. There you go. Now you don't really need this number, but I mean, if you wanna go ahead and throw it in there, you'll see why in a second. Let me just finish it up. Next one, element 2 is between nodes 2 and 3, right? So we're gonna have f2x, f3x. Okay. It's gonna equal to EA over L. It's also 15 times 10 to the 4. It's 15 times 10 to the 4. Cosine and sine, let's see, what is that? It's negative 0.6 and 0.8. So it's negative 0.6, 0.8, negative 0.6, 0.8. So sine switched, so 0.6, negative 0.8. I'm just following this formula, this one right here, okay? The signs just switch, 0.6 and negative 0.8. Cool. So we got, now it's between nodes 2 and 3. So it's the same vector, right? 0.4630, negative 0.035, 28, 0, and 0. There you go. Again, U2, V2, U3, V3, U1, V1, U3, V3. Just making sure you know which ones are those nodes. Go ahead and continue doing it right. F2x of element 2 now. That is 15 times 10 to the 4, parentheses, 0, 0, 0.6 times this number, that is gonna be 0.02778. And then finally 0.8 times this number, that's gonna give you, what is that? Is this right? 0.8 times, yeah, it should be negative, hold on, give me 1 second. Oh yeah, my bad, I was tripping. So I was using this number multiplying to this number, which is always confusing. It's negative 0.8 times this one. So it's 0.6 times that, and then negative 0.8 times this, which is also a positive. That is 0.02822. My bad, it's real easy to get mixed up. You gotta be careful. F2x of element 2, that's gonna give you 8,400, positive 8,400 pounds. Okay, and then if you do the same thing, F3x for element 2 is equal to negative 8,400 pounds. That's just telling you direction, right? It's if you remember the first chapter, second chapter, I can't remember, but they're always equal and opposite in signs. So next one, finally, we're gonna go ahead and do from nodes 3x to 4x. And that's gonna be EA over L. So it's 3 to 4, right? 3 to 4 for element 3. Because we use 90, if you would have done 270, remember, you would have had 4 to 3. That's why you gotta be real careful how you choose the angle. You gotta be consistent. So it's 375 times 1,000. So it's 375 times 10 to the third. And then what are the cosine and sine? 0, 1. Oh, thank God. Those are easier. 0, 1, 0, 1, 0, negative 1, 0, negative 1. And the reason we do x's is because now, I can't remember exactly, but if you look at the real formula when it's F3x, F3y, F4x, F4y, the columns, I mean the rows between these two, there's 0, 0, 0, 0. I don't know how it works, but for some reason you just use the x numbers here. So that's something I didn't know, but probably there's more reason to that, right? I don't know off the top of my head, I'm not gonna lie to you, but I just want to let you know that there's a reason we use the x's and not the y's. I just got to look into it more. But I'm being honest with you guys, I'm not gonna act like I know it all, but it's been like 2 years since I've seen this shit. So it's from node 3 to 4, so U3, V3, and then 4, 4, U4, V4. And there you go. We continue. Let's see. So it's F3x of element 3 is equal to 375, right, times 10 to the third. So it's 0 times that plus 1 times this. Oh, perfect. And that's it. 3528, because this is 0, 0. Oh, thank God. It makes it easier. F3x of element 3 is equal to, if you do the math, you'll get negative 13,230 pounds. My bad, I'm not sure you can see, but there you go. My handwriting gets a little sloppy when it's tired. If you do the F4x one just to do it, you'll get just a positive 13,230. Signs just switch. So now let's go ahead and verify this. So it says verify force equilibrium at node 3. So check it out. If you got 5,000 going to the right, that means you must have 5,000 going to the left, right? That's the only thing acting in the x direction. So, and the reason I use the x is, right, goes back to what I told you. We use the x numbers with this formula right here. So if you do that, you gotta add all the x's. In this case, just these right here, just one of them. You don't add both because they're just equal and opposite. So if you add 8,400 plus 66, that's like 8,500 minus 13,230. I forgot what it was exactly. I don't have my calculator, but you'll get close to negative 5,000. I think it was like negative 4,600, something like that. And that makes sense. The reason it's not exact is because we rounded like shit, right? All these numbers and then all the next numbers. It's just a lot of rounding. But yeah, it is negative 5,000, so it is verified. That's pretty much it to the problem. It's pretty long. It's the first time doing using the force, write this equation. So I guess if you want to learn it, here it is. But there you go. That's the bottom. It's the top part of the back page, and then finally that's the top part, bottom part. And again, just remember to make sure you know how to determine the angles. That's really, really important. But yeah, you'll be all right.